Hey kids, welcome to section 8.2 Z-test for the mean. Today we're going to learn how to test means when sigma is known using the Z-test. So this is our first hypothesis test that we're learning about. We went over the 5 steps in the last section. Now we're going to apply them to a particular situation. So this is called the traditional method for hypothesis testing. The Z-test is defined formally as follows. So there are two assumptions that need to happen in order for you to be able to complete a Z-test for a mean when sigma is known. The first one is the sample is a random sample. That's pretty much been a necessity for almost everything we've done so far. Number two, the sample size has to be greater than or equal to 30, or the population has to be normally distributed if the sample size is less than 30. So it's always good to have a random sample and pretty much make sure it comes from a normally distributed population. Now, the Z-test is a statistical test for the mean of a population. It can be used either when n is greater than or equal to 30 or when the population is normally distributed and sigma is known. So most important is that sigma is known. The formula for the Z-test is, so this is called the test statistic. This comes up in the third step of the hypothesis test, also called the test value. And we're going to see today how it's going to be very useful in determining our outcomes. Notice that z is equal to x bar minus mu over sigma over root n. So we're taking the sample mean, subtracting the hypothesized population mean, and then divide by the population standard deviation over the square root of the sample size. I put the 5 steps of the hypothesis test down here again, just to remind you. Step 1, state the hypotheses and identify the claim. Step 2, find the critical value, and also this is where you can graph. Step 3, compute the test value. That's the equation that's right up above. Step 4, make a decision to reject or not reject the null hypothesis. And then finally, step 5 is summarize the results with a sentence. So let's just review one more time how we make those decisions. These 2 dots up here at the top remind you of error. When the null hypothesis is rejected, there is always a chance of a type 1 error. That's your alpha. When the null hypothesis is not rejected, there is a probability of a type 2 error. That's your beta. Remember, your alpha plus your beta equals 1. For now, it's only necessary to realize that the probability of a type 2 error exists when the decision is not reject the null hypothesis. Also note that when the null hypothesis is not rejected, it cannot be accepted as true. There is merely not enough evidence to say that it is false. So you can never accept. You either reject or you not reject, but you never accept. This guideline may sound a little confusing, but the situation is analogous to a jury trial. So over here, I put the 4 outcomes of a jury trial: that you can be innocent and still be convicted. That would be a type 1 error. You could be innocent and you could be acquitted. That would be a correct decision. You didn't commit the crime, so you don't have to do the time. Or you could not be innocent and be convicted. That would be a correct decision. And the final one, not innocent and acquitted, that is a type 2 error. And that means that you did the crime and you are going to do the time. All right, so let's see how all of these steps now we put together to do a formal hypothesis test. This one is about intelligence tests and IQ. In Pennsylvania, the average IQ score is 101.5. The variable is normally distributed and the population standard deviation is 15. A school superintendent claims that the students in her school district have an IQ higher than the average of 101.5. She selects a random sample of 30 students and finds the mean of the test scores is 106.6. No, 106.4, sorry. Test the claim at alpha equals 0.05. All right, so before we start our steps, let's gather our information over here. We're going to need an X bar we're going to need a mu, we're going to need a sigma, and we're going to need an n. X bar is our sample mean, so we have a random sample of 30 students. There's our n. And the mean of those test scores was 106.4. That's our X bar. We have a population standard deviation of 15. That's our sigma. And the average IQ of everybody in Pennsylvania, 101.5, is our mu. All right, so now we go into step one. Step one is to name your hypotheses and identify the claim. So we need the null hypothesis and we need the alternative hypothesis. So we have three variables to choose from for our hypotheses. You've got mu, you've got p, and you've got sigma. Since we're talking about the mean here, we're going to use sigma. Hint, that's what everything in this section is going to use. The null hypothesis is always mean equals, and the alternative is mu. So in order to put the rest of the hypothesis information in, all I got to do is look over here. I see my mu is 101.5, so that's still my mu. Also in the problem, the school superintendent claims that her students have a IQ higher than the average, so our alternative hypothesis is that mu is greater than 101.5, and this is also the claim. That is what we are trying to support or not be able to support. Okay, step two is to draw a picture and find the critical value. So in this situation, since we are trying to look at greater than 101.5, we're going to be shading on the right. Our alpha is 0.05. Now I need a critical value, which is z alpha over 2. I get this by inverse norming. So inverse norm. However, I can only inverse norm area to the left, which means if the right shaded side is 0.05, my left unshaded side is 0.95. So I'm going to inverse norm 0.95. This is going to give me a critical value of 1.64. It's a positive critical value because it's on the right. If it was to the left of the mean, it would be a negative critical value. All right, now we have to calculate in step 3 the test statistic. So z equals x bar minus mu over sigma over root n. So I'm going to take my x bar, which is 106.4, subtract my mu, which is 101.5, over my sigma, which is 15, divided by the square root of n, which is 30. If I type this into my calculator and round to 2 decimals because it's a z-score, I get z equals 1.79. So this test statistic tells us that I'm going to draw a little arrow. So here is my 1.64. That critical value cuts my graph into a shaded and a non-shaded. The shaded is the critical region, and the non-shaded is the OK region. I don't know if I want to say OK. It's like non-critical. So when I have a cutoff, a critical value of 1.64, and then I take a look at my test statistic, and that test statistic is going to be in the shaded region. Since it's in the shaded region, that's the critical region. When it's in the shaded region, I'm going to reject the null hypothesis. So, since 1.79 is in the critical region, we are going to reject the null hypothesis. We reject the null, the h sub 0. So again, that critical value of 1.64 cuts the graph into 2 sections, a shaded and a non-shaded. The shaded region is called the critical region. If we end up in there, we're going to reject the null hypothesis. If we end up in the non-shaded region, that's the OK region, And we are not going to reject the null hypothesis. Not reject the null. Okay, now, since we are rejecting the null hypothesis, we need to look at our claim and see that since we are rejecting the null hypothesis, that means the evidence that we found being greater is going to support the claim that the test scores are higher, or that the IQ is higher than 101.5. So there is enough evidence to support the claim that the students' IQ scores are greater than 101.5. So we calculated this evidence off of the sample. The evidence put us into the critical region. Since we rejected the null hypothesis, we know that it's not going to be equal to 101.5. So therefore, we can support our claim that it is greater than 101.5. We have enough to say that it's not 101.5, so we can support it is 101.5. We also have a table that we can look at. This table requires that, here, let me zoom in on it. So this table right here needs to know if the claim was the null or the alternative hypothesis, and then if we rejected or do not reject the null hypothesis. And so back in our picture, the claim is the alternative and we reject the null. So the claim is the alternative and we reject the null. So there is enough evidence to support the claim. So this table can help you kind of gather all your information to write that final sentence. All right, let's take a look at the next one. This one is about SAT tests. So for a specific year, the average score on the SAT math test was 515. The variable is normally distributed and the population standard deviation is 100. The superintendent wishes to see if her students scored significantly below the national average on the test. She randomly selected 36 student scores as shown. At alpha equals 0.10, is there enough evidence to support the claim? Well, we need 4 variables in order to keep going with the problem. We need an X bar, we need a mu, we need a sigma, and we need an N. Well, X bar is going to require me to put all of these into my calculator, which I already did for us guys, and I got 509.0. So I put all of these values into my L1, and then I ran a 1 var stat calculation. I rounded to 0.0 because my data didn't have any decimals, so I knew that my mean had to have one more. My mu is my population mean, which was 515. My sigma is my population standard deviation, which is 100. And my n is the number of values, which is 36. So now I'm ready to start my steps. First step is to identify the hypotheses and the claim. So my null hypothesis and my alternative hypothesis. My null hypothesis is mu equals 100. My alternative hypothesis is, since it's below, I'm going to say mu is less than 100. And this is the superintendent's claim. Now I can draw a picture and find the critical value. Since I am drawing a alternative hypothesis is less than 100, I'm going to shade less than 100. My alpha of 0.10 is going to go directly to that shaded critical region. I can now find my inverse norm of the value to the left, which in this case is 0.10. This gives me a critical value of negative, because it's to the left of the mean, 1.28. So that's the value that's going to separate the critical region from the non-critical region. All right, let's take our data and calculate the test statistic. Z equals x bar minus mu over sigma over root n. So my x bar is 509.0. My mu is, wait, why did I put 100 here? That was dumb. That should be equals 515. I don't know why I put that there. Sorry, kids. Ugh. Well, your teacher is human. All right. 509.0 minus 515 over 100. Excuse me, sorry. Over root 36. All right, so I type this into my calculator. I get a test statistic of negative 0.36. Okay, so now we have to figure out if our test statistic is in the critical or non-critical. So let's see, here's the cutoff, which is negative 1.28. 0.36 would be to the right, which means it's in the non-shaded region. So since negative 0.36 is in the non-critical region, we do not reject the null hypothesis. So we are not rejecting the null hypothesis, which means we don't necessarily think it's wrong, which means we don't have enough evidence to support our claim. We can also look on the table. Our claim is the alternative and we are not rejecting. So the claim is the alternative and we are not rejecting. There is not enough evidence to support the claim. There is not enough evidence to support the claim. That the students scored significantly below 515. So since we're not rejecting the null hypothesis, we can't for sure say that it's going to not be 515, which means we can't say for sure if it's going to be less than 515. All right, let's see another one. This one has to do with rehabilitation for our stroke victims. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $26,343. The standard deviation of the population is $3,251. At alpha equals 0.01, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different from $24,672? All right, so we have x bar, mu, sigma, and n. X bar is our sample mean. Our sample mean is going to be 26,343. Our mu is our population mean, which is 24,672. Our population standard deviation sigma is 3,251. And our sample size n is 35. Step 1, write your hypotheses. So our null and our alternative hypotheses. We are using mu So we have mu equals and mu. Our mu is equal to 24,672. Our alternative hypothesis, well, they're trying to see if it's different from, so that means not equal to. So we don't know if it's greater, we don't know if it's less, but we just know it's not equal to, it's different. Then we draw our picture. Since it's a not equal to, we are shading both sides. Well, I guess we should also say that she is claiming that they are different. All right, so our alpha is 0.01, but that alpha needs to be split in between both of the shaded regions. So if I divide 0.01 by 2, I get 0.005, and then I also have a 0.005 over here. When I find the critical value, I'm going to inverse norm 0.005. Now, when I get my answer, I need to make sure I have two answers. So I'm going to have plus or minus, and then you get 2.58. So you know that it's different. You don't know if it's greater, you don't know if it's less, but you know that it's different. So therefore you have two critical regions. You split the alpha into two, and you have two critical values, plus or minus. We do only calculate one test statistic though, because we only have one set of data. And so our test statistic, x bar minus mu over sigma over root n, we've got 26,343 minus 24,672 divided by 3,251 over square root 35. This gives us a test statistic of 3.04. So remember that our critical values were a positive and a negative 2.58. A test statistic of 3.04 would put us in the shaded region on the right. So since 3.04 is in the critical region, we reject the null hypothesis. We reject the null. So since we're rejecting the null, that goes in our way because that adds to the support of our claim. So notice that our claim is the alternative and we reject. So the claim is the alternative and we reject. There is enough evidence to support the claim. So our sentence, there is enough evidence to support the claim that, and our claim is that the average cost is different, that the average cost is different than 24,672. I mean, based on the sample data that we got, we could maybe in further investigations see if it's always going to be greater, or we could continue to see that it's just not the same. All right, let's keep going. Number next. This one's about college tuition. A researcher wishes to test the claim that the average cost of tuition and fees at a particular four-year school is greater than $5,700. She selects a random sample of 36 four-year public colleges and finds the mean to be 5,950. The population standard deviation is 659. Is there enough evidence to support the claim at alpha equals 0.05? All right, so I need x bar, I need mu, I need sigma, and I need n. So x bar is our sample mean. We sampled 36, that's our n, and we found the mean to be 5,950. There's our x bar. Our population standard deviation sigma is 659, and our population mean is 5,700. That's our mu. So now we need our hypotheses. We are dealing with mean, so we have mu equals and mu. Our mu is equal to 5,700, and the first sentence claims that it's going to be greater than 5,700. That's our claim. So we draw our picture. It is greater than, so we're shading on the right. Our alpha is going to go all to here, so 0.05. However, we need the right side in order to inverse norm, not 995. Duh, Yanka. Just 95. Okay, so our critical value is going to be the inverse norm of 0.95. So critical value is, since it's on the right-hand side, is positive 1.64. That's our cutoff. Okay, so now we need to do a test statistic for our data, x bar minus mu over sigma divided by root n. So x bar is 5,950 minus mu, which is 5,700, divided by sigma, which is 659, over the square root of n, which is 36. This calculation gives me a critical value of 2.28. So our critical value is 1.64. 2.28 puts us in the critical region. So we are going to reject the null hypothesis. So since 2.28 is in the critical region, we reject the null hypothesis. So if we're rejecting the null hypothesis, then there is enough evidence to support our claim. We can check with the graph. We have an alternative claim and a reject. Alternative claim and a reject. Enough evidence to support the claim. There is enough evidence to support the claim that, and our claim was that the cost is greater than, that the cost is greater than 5,700. All right. We have a different one in the next slide. The claim is going to switch hypotheses. Ooh. Wind speed. A researcher claims that the average wind speed in a certain city is 8 miles per hour. A sample of 32 days has an average wind speed of 8.2 miles per hour. The standard deviation of the population is 0.6 mile per hour. At alpha equals 0.05, is there enough evidence to reject the claim? Well, we need an x bar, a mu, a sigma, and an n. We have a sample size of 32. We have a standard deviation of the population to be 0.6. We have a sample mean of 8.2. That's our x bar, which means our mu is 8. So we have our null and our alternative hypothesis. We are dealing with means, so mu's. We have a mu equal 8 as our null hypothesis, and our alternative hypothesis is, well, it doesn't really say greater than or less than, so we're going with not equal to. And notice this time that our claim is the null hypothesis. All right, so we're going to draw a picture. Our alternative is not equal to, so we have two shaded regions. Our alpha of 0.05 needs to be split between both regions, so each one gets 0.025. When I calculate my critical value, I want to make sure that I inverse norm 0.025. This also gives me 2 critical values since I have 2 critical regions. So I have plus or minus, and the critical value will be 1.96. I only calculate one test statistic, x bar minus mu over sigma over root n. So we have 8.2 minus 8 over 0.6 over root 32. This gives us a test statistic of 1.89. So our critical value 1.96 cuts us into 2 sections. 1.89 is not in the shaded region, and so therefore we will not reject the null hypothesis. So since 1.89 is not in the critical region, we do not reject the null. So we're not rejecting the null, which means there might be evidence to our claim. So let's take a look. Our claim is the null this time, and we are not rejecting. So null claim and not rejecting. So there isn't enough evidence to support it, but there's not enough evidence to reject it. So there is not enough evidence to reject the claim that the speed is 8 miles per hour. So since we're not rejecting the null, and the null is our claim, then we're not necessarily going to reject the null. So that's how we get our final sentence. All right, one more problem, the application problem. This one's about car thefts. You recently received a job with a company that manufactures an automobile anti-theft device. To conduct an advertising campaign for the product, you need to make a claim about the number of automobile thefts per year. Since the population of various cities in the United States varies, you decide to use rates per 10,000 people. The rates are based on the number of people living in the cities. Your boss said that last year the theft rate per 10,000 people was 44 vehicles. You want to see if it has changed. The following are rates per 10,000 people for 36 randomly selected locations in the United States. Assume that sigma equals 30.3. All right, so using this information, answer these questions. What hypotheses would you use? Okay, so we've got our null and our alternative. Well, let's see some data. We got an x bar, a mu, a sigma, and a root n, or just an n. So what do we know? Well, we know that sigma is 30.3. We know that n is 36. We know that the sample mean was 44, which means the mu has got to be, wait, no. Your boss said, oh, duh. We need to actually calculate the sample mean. Duh, Yanka. The mu is going to be 44. That's what they are saying was the previous. If I type all of this stuff into my calculator and do one var stat, I get an x bar of 56.0. So our null hypothesis would be mu equals 44. Our alternative hypothesis, since we want to see if it has changed, is going to be mu does not equal 44. And this is going to be my claim. Number 2, is the sample considered small or large? Well, out of all the cities in the United States, only picking 36 is going to be super, super small. However, since it's greater than or equal to 30, it's adequate enough. So we're going to say the sample is large enough. And we'll put in parentheses that it is greater than or equal to 30. What assumption must be met before the hypothesis test can be conducted? It has to come from a normally distributed population. So the variable should be from a normally distributed population. I already know that the first assumption is met because I was told in the problem that we randomly sampled the 36 locations. So that's assumption 1. And then assumption 2 is that it's got to come from a normally distributed population. Number 4, which probability distribution would you use? We're going to use the Z distribution. That's why our critical values have been Z alpha over 2s. Number 5, would you select a 1 or a 2-tailed test? Why? Well, remember our claim is not equal to, and so therefore we are graphing a 2-tailed test. So we use a 2-tailed since the alternative hypothesis H1 does not, since H1 is not equal to. What critical values would you use? Okay, well, if we draw our picture, we've got shaded on the right and shaded on the left. Our alpha was 0.05. So that means that each one of our shaded regions is 0.025. That means our critical value is going to be plus or minus, and we'll inverse norm the 0.025, and we get 1.96. We need to compute the test statistic. So that's x bar minus mu over sigma over root n. Our x bar was 56.0. Our mu was 44. Our standard deviation was 30.3. And our sample size was 36. This gives me a test statistic of 2.38. So now we look back up here. Our cutoff value was 1.96. 2.38 is in the shaded region, so we are going to reject the null. So since 2.38 is in the critical region, we reject the null hypothesis. And remember that our claim was the alternative hypothesis. So since we are rejecting the null, we have enough evidence to support the claim. We can check one more time. Our alternative was our claim, and we were rejecting, so there is enough evidence to support the claim. So our brief statement summarizing, there is enough evidence to support the claim that, and we were initially looking to see if the number of thefts has changed, and so we have enough evidence to support the claim that the number of thefts has changed. We don't know how. We don't care how. All I know is that it's changed. All right, kids, that's the end of section 8.2. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.